The last thing I want to talk about before we get into the polyarc is actually the R&D and the customer engagement. So these things actually go hand in hand with this new lean startup agile approach. So if you want to sell something, which you have to do at a company because we need to make money, otherwise I won't be here in 6 months, talking in front of you, is you need to find your customer's pain point. You need to find something that people will actually buy. And you do that in tandem with R&D so that you can tailor your product to your customers and finally launch a product that meets your customers' needs. Okay, so the pain point for the polyarc reactor actually came from Paul and his students when they were studying cellulose pyrolysis, which is just a fancy chemical engineering term for heating something. Right, Paul? And the pain point that they had was that they were analyzing this heating of cellulose and they were degrading it to a bunch of products to find chemicals and fuels. And when they looked at all the products, they got this GCFID spectra. And this is how you analyze products with carbon in it, right? You use a GCFID. And when they look at the spectra, they saw hundreds of different peaks indicating hundreds of unique compounds in there. And the pain point was that in order to quantify this spectrum and in order to thus understand the kinetics and what's happening with pyrolysis, they needed to calibrate each one of these peaks for each compound. So they needed to know what the identity of that peak was, what chemical compound, what the response was in the GCFID, and then be able to integrate that peak and separate it so that they could actually quantify it. So to understand why this is such an insurmountable task for something like that, we have to understand a little bit about how the GCFID works. So very briefly, a GCFID, a GC is just a glorified oven, right? A gas chromatograph. It's an oven that heats, cools rapidly, and then holds a temperature. And inside of that oven, we have this column, which does all the separation. So you send a mixture in, and then you separate everything into its individual components. And those individual components then flow to the detector, which can either tell you the identity or the quantity of what's going into that detector. The most common detector is actually the flame ionization detector, and this is because of the many benefits of that detector. And now the flame ionization detector is actually quite a simple detector. It's just a flame, as the name states. That's a hydrogen and air flame. And you burn the sample or the individual components as they come up into that flame. And when you burn them, you create these ions, these carbocations. And about 1 in every million carbon atoms that goes into that flame creates one of these ions. And then you just take an ammeter and you measure the number of ions, because there's electrons that have to balance it. You measure the number of electrons that go through, and that's a signal that's proportional to the amount of sample that's gone through that detector. Now the FID, as I said, is great for a number of reasons. It's got a huge range of sensitivity and it's very linear response. But like other detectors, the response of the FID depends on the identity of the molecule. So right here I'm showing the sensitivity of the FID measured by Dietz in 1967 of different molecules in the FID, sensitivity per carbon atom. And as you see for methane, pentane, heptane, really any linear alkane, the response is about 1. It's about unity. And that's because all those carbon atoms have CH bonds, CC bonds that are very similar. But when you start to get to things with oxygen, like methanol, now you have a 23% less response per carbon because of that alcohol group. Formic acid is even worse. It's a 1% of the response. And there's some molecules that you really just can't see. CO, CO2, for example. So in order to now study these compounds, you need to calibrate the FID. And these response factors can actually change depending on which FID you're using, because the reason inside of this flame you're actually doing hydrogenolysis reactions. And those hydrogenolysis reactions that split the molecules depend on the temperature, the hydrogen, the air that's in there. So you need to calibrate your FID before each experiment. Now what Paul and his students realized was that if you put a tiny reactor, so this is a picture of that polyarc, if you put a tiny reactor after the column but before the detector, you could convert everything, I forgot I have this, you can convert everything into methane before reaching the detector. And what that means is that all of that your responses are going to be one. They're all going to be the same because you just have methane going to the detector. So to illustrate this point further, I'll give you two examples. In the first example, I want to inject an equal carbon mixture of isopropanol and inheptane. And when I put those into an FID without the reactor present, I see that the area of the isopropanol, again, there's just as many carbons in this as there is in heptane. I see the area of isopropanol is 64.3% less than that of heptane. And that's because directly this alcohol group right here decreases the probability that that's going to form a carbocation. If instead we put a polyarc reactor into that GC, we actually see that the area of the two peaks are the same, because all the carbons have been converted to methane, and now the probability to form a carbocation is the same. So as another example, with a few other molecules, we see the same result. In the FID, the peak area ratios differ by up to 200%. So this ketone group and acetone, that decreases the propensity to form carbocations even further. But when we put the reactor in there, all these response factors or all these sensitivities go to 1. So no longer do we have to calibrate our GC because all the response factors are the same. Now that might be a small time saving for some of these, but it's a huge time saving when you have, more than 8 or even 100 compounds, which you do with cellulose or MTG or Fischer-Tropsch. Another benefit is that if you have overlapping peaks, you can integrate the entire, so let's say you can't do the separation with your column, you can integrate the entire mixture of peaks and get a total carbon number. And that goes for, even if you don't know what this peak is, you can at least get a carbon balance. So if you wanted to study the total volatile organic carbon content of something, you could just integrate all the peaks and get a total number of carbons.